Hi everyone, my project topic is stress reduction behavior in metal incorporated carbon films. Different functionals and basis sets are tested. Amorphous carbon films attract lots of interest because of their hardness, chemical inertness, optical transparency, and biocompatibilities. Some applications include plastic, healthcare industries, as well as in the fields of gas and water filtering. However, amorphous carbon films have high residual compressive stresses, which could lead to spontaneous delamination. Uh, Delamination is shown on the left. It happens when stress experienced by the composite initiates cracks. It will cause significant damages, and it is a main obstacle to carbon films application. One of the solutions for solving the delamination issue is incorporating of transition metals. Several studies have proved the potential of this method. For example, experiment found that internal stress was significantly reduced in the copper incorporated DRC films and titanium incorporated amorphous carbon films. Computational study has also been conducted and found that stress reduction behavior in metal incorporated amorphous carbon film using first principle approach. In that research, PBE and double zeta polarization were used. Now I'm gonna talk about some observations from previous computational work. The left plot, the y-axis represents the energy difference before for energy difference before and after changing the bond angle from 109.5 degree to 19 degree. And on the right is the formation energy of metal incorporated carbon films. One observation is that in the absence of a metal atom, the total energy increased drastically as the bond angle deviated from the equilibrium value of the tetrahedral bond. Another observation is with the metal atom located at the center of the tetrahedron, the increase in the total energy due to the distortion in bond angle was significantly reduced. And another one is the metal atoms giving a small increase in the total energy by the bond angle distortion usually correspond to those having large formation energies. For my project, I was trying to answer two questions. One is how different functionals and basis sets affect energy calculations. Second is will other functionals and basis sets validate the conclusion from previous work. In this project, I use OCAR to optimize the geometry and calculate the energy. OCAR is an ab initio quantum chemistry program that can be used for DFT calculations. I tested two basis sets. They are DF2 SVP, which is a one-less double zeta basis set, and DF2 TZVP, which is a valence triple zeta basis set. I tested three functionals. They are PBE, which is GGA, PBO, a hybrid functional, and WB97X, a hybrid functional. The model I used for simulation is tetrahedral model, which is shown on the top right. The four carbon atoms are arranged as a tetrahedron with a carbon or metal atom at the center. Below is another is the model for 19 degree bond angle. Three of the carbon metal bond angle were distorted to 19 degree, and the energy difference of the tetrahedral model and 19 degree model were used to represent the stress caused by distortion. different functionals. PBE is one of the most universal GGA. It can be applied to both molecules and solid, including metals. Another one is PBE0. It makes the PBE energy and heart rate Fock exchange energy in a set of 3:1 ratio. Plus for PBE correlation energy, the energy equation for PBE0 is shown here. For WB97X, it is a long-range corrected hybrid. It included long-range part of the exchange correlation energy. Hypotheses for this paper are listed below. First, energies calculated using different functionals will have a systematic tendency. For example, bonding distances are usually overestimated by a certain percent by PBE. They are non-empirical functionals, and errors of non-empirical functionals usually have a systematic tendency because they use only general rules of quantum mechanics and special limiting conditions to determine the parameters in a general form. They can be considered controlled extrapolations away from known systems, and so their reliability for new systems and properties can often be predicted or at least understood. Another hypothesis is large basis set will generate low energies considering additional degrees of freedom. The optimization procedure is done in the infinite space of real-valued functions that represent the density. However, by choosing a finite basis, you constrain this search space. And the more complete your basis size, the more flexibility you have to find the ground state density, because the density is built from the single particle orbitals expanded in the given basis. In this slide, the comparison of energies calculated using different functionals and basis size are shown. Is for the tetrahedron structure 109.5 degree bond angle. What I did here is calculate the energy difference between WB97X PBE with large basis size and PBE0 with PBE calculations. There are some observations here. One is there is a systematic tendency. For example, the PBE, the calculation with large basis size generated lower energy. It makes sense since large basis size create a high degree of freedom. And another systematic tendency is WB97X generated lower energies. It makes sense too, since WB97X is a higher level functionals compared to PBE. Another observation is that the performance of PBE0 and PBE functionals are very similar. It's a super surprising result for me, considering the relatively significant differences in those two functional forms. The energy difference for 19 degrees structures show the similar trend. Finally, here is the relationship between energy differences caused by distortion and the formation energies of the metal incorporated carbon films. These results were calculated using energies calculated by WB97X functionals. It validated the previous computational work. Absence of a metal atom, the total energy increased drastically as the bond angle deviated from the equilibrium position. And with the metal atom located at the center of the tetrahedral, the increase in the total energy was significantly reduced, and the ability to reduce the stress energy is related to the formation energy of the metal incorporated carbon films. Impact of this project when further validated the conclusion of previous work that metal incorporated carbon films could reduce stress, and the ability of reducing stress is related to the formation energy. Another impact is provide an understanding of the performance of different functionals and the basis set. Now I'm going to talk about some possible future works. First, in this project, only a single tetrahedral structure was considered. So the strain energy term induced by larger atom incorporation was not considered. In the future, a periodical structure could be tested. Another future work is on comparing the simulation result with experimental data. Also, in the future, study of the defective structure could be conducted since no amorphous carbon film is defective-free. And this is my presentation today. Thank you.